Okay, a short video talking about implicit differentiation. So what do we mean by that? What are we going to do with it? What I want to do before we tackle something like this using implicit differentiation is just do a little bit of background. We start off with something that's nice, that I can differentiate easily. If I have y equals x squared, I'm happy with that. Seen it before. I can differentiate and find dy dx is 2x. I'm happy with that. What about if it's perhaps not quite as nice as that? What about if it's something like that? Y squared equals 4x cubed plus 11, let's say. Well, I might want it in this form. I might want to write y equals and then get everything else to the other side because I'm happy, I know how to differentiate that. I could deal with this. I could perhaps take the square roots of both sides, but it's not that straightforward. I've got to be careful. If I square root it, I've got a plus and a minus. And, well, I could do it perhaps, but what about another time if it was about if it's something like that? At some point I'm either going to say this is going to take forever to rearrange to get y on its own so I can do the work I like to do, or actually it's impossible, I can't see how I can do it. So we'd like another way so we could deal with questions like this, being able to differentiate and find dy dx. So that's what I want to talk about. So what I want to do is to work through this using implicit differentiation. What we're actually going to be doing is using the chain rule, but I'm not going to go into the details of that. I'm just going to show you how we can make it work. So let's have a look at this, and I'm going to start off doing the easy bits. So here's a function of x, sine x. I know what happens if we differentiate sine x. We get cos x. I've got another x term here. I don't happen to differentiate that. I get 2x. Put the equal sign back in. So I'm leaving the tricky bits and I'm doing the nice bits. I'm going to leave that for a second and I'm going to jump to the end. I know what happens if I differentiate with respect to x, I get a 1. So I get a plus 1. Now I've got to deal with these tricky bits. They're functions of y. So as I say, what we're doing in the background is we're using the chain rule. But the good news is, I'm going to do this by differentiating with respect to y. So if I had x squared and differentiate with respect to x, I'd get 2x. So I differentiate this with respect to y, and I'm going to get 2y. And this is where the chain rule kicks in. And I say, well, really, it was with respect to x. And I can deal with that by multiplying by dy dx. So if it's not a function of x I'm differentiating, I can still cope with it. I differentiate it with respect to y times by dy dx. So I think I can do that over here with this other function. If I had cosine of x and I differentiated it, I'd have minus sine x if I differentiate with respect to x. So if I differentiate this with respect to y, I should get minus sine y. Seems simple enough. However, it's with respect to x. So I have to use the same rule I used over here, and I multiply by dy dx. Now, I think I've dragged that out and made it quite long-winded. The good news is, do all the functions of x, as you would, do the functions of y, and then multiply by dy dx. And now our calculus is finished. If I can rearrange it, to get dy dx on its own, I've finished. So what I want to do is get any term with a dy dx on it to one side and any without to the other. So I'm going to keep this left hand side for my dy dx term. So I need to drag this one across here and then perhaps get rid of the cos x and the 2x to the other side. So 2y dy dx. I'm going to drag this minus sine of y dy dx to this side where it becomes a plus sine y dy dx. And I'm left with that 1 on the end. And now I'm going to take over any term that's not got a dy dx. So the plus cos x becomes minus cos x, and the plus 2x becomes minus 2x. We're pretty much there now. Both of my terms on the left have a dy dx, so I can factor that out. I can drag it out to the front, if you will. So I can say it looks like that. Two terms, dy dx in common, so I drag it out to the front and I'm left with 2y plus sine y. And all I want to know is what on earth is dy dx. So I just divide both sides by this bracket, or in other words I drag that bracket down to the bottom of the right hand side. So just about squeeze it in. So dy dx equals 1 minus cos x minus 2x all over 2y plus sine y. And that's how we can use implicit differentiation to do something otherwise which would be either very difficult or actually impossible to rearrange. And all the other rules apply. You can use the product rule, the quotient rule. All these rules could still be worked with inside implicit differentiation. So perhaps if you try some more examples. Okay, so that's that question done. Thanks for watching.